10 problems up here for you to work on to get started with. So to begin with, work on these, get your answers. We'll compare answers on that and explain why they are the way they are. Then we'll do this one thing on phase diagrams, and then we'll just be open for questions on whatever you want to cover. Now, as far as announcements go, your final exam is on Monday, starting at 2:30. Not our usual time. Don't be coming in at 3:05 thinking you're doing good. You'll miss a significant chunk of your time. It's at 2:30. It is a multiple choice Scantron test. You need a pencil for that, not ink. So if you're in the habit of using ink on exams, you will need to make sure to have a pencil there.
How many questions?
50? I think it's 50. Yeah, it's definitely 50.
Question final.
A one question final. 200 points. You get it or you don't. We don't get to leave early, right? That's going to be good.
1, 0. The finals. I think that's a marker. Leaders are normally leading. It's like 1 times 10 in the third or sixth.
One thing that everybody needs to go back and look at is those metric prefixes. We've used milli and kilo a lot, but we've kind of gotten away from micro and nano and ones like that. Make sure you review them. less than half of your final exam is going to be mathematical. And what math you do have is going to be pretty short, because you're going to have, on average, like 2 minutes per question to work with. On every exam, you have conceptual stuff and mathematics and short calculations and then long calculations. You're not going to have anything comparable to those long calculations. Another announcement, for those of you that are considering something in the medical line of work, they're having a next semester is a medical terminology class in Spanish. And no Spanish, no previous Spanish is required. So if anybody, if you are going the medical route, they will have something useful and beneficial to you in the future. Let's go ahead and work through the ones on the left-hand board, then I'll give you a little bit more time to finish the others. And I guess let's start with the ones that are not mathematical. Which element has 3 unpaired electrons? So that's going back to electron configuration and being able to read parts of the configuration off the periodic table. Aluminum would have a configuration, abbreviated configuration of neon core 3s2 3p1, correct? How many unpaired electrons is that?
3.
That's 1. Because these 2 and the s are paired up. You've got a single s orbital, p orbitals come in groups of 3, but this is 1, 2, 3. All right, now it has 3 valence electrons, but it's not asking you about valence electrons. It's asking you about unpaired electrons. And for aluminum, it's just got that 1. So it's not aluminum. Chlorine is also a 3rd row element. So for chlorine, we're looking at neon core 3s2 3p5. So here's the s, 1, 2. Here's the set of p, 1, 2, 3, 4, 5. That's also 1 unpaired electron, correct? So it's not either of those. Has everybody made note of this? Start time 2:30, all right. Praseodymium, this is element 59, so we're looking at a xenon core. 6s2 5d1 4f2. This is the S. This is the D. And it's that quirky little thing where you don't even fill up the D before you go on and you start putting into the F. So I didn't leave myself much room for this. 1, 2, 6, 7 for the F. There's 2 electrons out there. So that's the one. It's got 1 unpaired electron in the D, 2 unpaired electrons in the F, but that's a total of 3 unpaired electrons. Iron, if we want to go ahead and put that up here, might as well. Argon core, 4s2, 3d6. This is the S. This is the D. How many unpaired electrons for it? 4. Question about this one being praseodymium. All right. Let's do this, the orange one next. And the key word here is contains. Which one contains ionic bonds? What kind of element is sulfur? Non-metal. Oxygen, non-metal. That's all covalent bonding internally, correct? Now sulfate will bond to other things by ionic bonding, but internally it's all covalent. contains. Not which one is capable of ionic bonding, but which one contains ionic bonds. This one does not, okay? This is purely covalent internally because it's all non-metal. Which, I guess, rules that one out too, right? Which also rules out that, and which also rules out that, because everything up here is non-metal. Is that right? No, it's not.
Because NO3 is,
NO3 is generally a polyatomic ion. And if this had been KNO3, that would contain ionic bonding. But hydrogen is a non-metal, and that's covalent. Remember, hydrogen is that quirky one, right? It's this one. And hopefully you remember, if nothing else, you remember from your naming assignments in lab that ammonium is a positive 1 charge. So ammonium with chloride, even though that doesn't look ionic because you don't have metals in there, that's still ionic. None of these really looked ionic, I guess, except maybe that one, and that's a little deceptive. But this is the one that contains ionic bonds. Because ammonium was probably your only example of a polyatomic cation that you had in your naming system. Now, since then, we've had hydronium when we were doing ionization reactions, but ammonium is a cation. So which one contains ionic bonds would be the ammonium chloride. Any question about that? All right. Microliters in a milliliter. The milli prefix means what? Numerically. 10 to the negative 3. So we convert out of milliliters into normal liters. And then we want to go from normal liters to microliters. What's micro mean numerically? 10 to the negative 6. So you do the math here and it ends up being 1,000. But if you're not careful with your calculator, you could get a false answer if you're not careful about how you type that in. And that's very easy to do. Exponents like this, negative exponents, and well, any exponent really, in the denominator leads a lot of people into math errors. So don't let that happen to you on the test. All right, practice that so that you know the little peculiarities of your calculator. It ends up being 1,000. Any question about that? All right, this one, we're looking for how many atoms. We start with our 25 milliliters. And we have a density. So 1 milliliter is 0.789 grams. So density gets us out of milliliters and into grams.
I did that already. If you want it.
Have you got the answer?
Yeah. 46.0694.
46. Oh, the molar mass?
Yeah.
46.0694.
Yeah. Sorry.
No, that's good. Thank you. CH3, CH2OH, 6.022 times 10 to the 23rd. And this is where people typically mess up. What's wrong with this? Why is that wrong? I'm telling you, this is a very common error. What's wrong with that? Go ahead.
Because that'll give you molecules.
Good. It goes back to, it's not necessarily a problem with the math, but it goes back to our definitions of atoms and molecules. The smallest particle of a compound is the molecule. And so when we're relating moles of ethanol by Avogadro's number, that's not going to be atoms, that's going to be molecules, which means we still have another step to go, where we look at how many atoms are in the molecule. Which is what? We got 2 carbons, we got 3, 4, 5, 6 hydrogens, 1 oxygen, that's 6, 7, 8, 9. 9 atoms in that molecule. Very common mistake, people omit that last step. And more than likely, we will anticipate that, and whatever you got from these 4 terms is going to be either A, B, C, or D. All right? That's more a matter of being comfortable with the difference between atoms and molecules than it is a mathematical thing. Question about that, especially that last step. Yes?
You're saying without the last step, that answer's gonna be on
Very likely. And without that last step, your answer would really be molecules of the ethanol, not atoms, individual atoms of the elements. So when you're reading the question, watch the wording carefully.
But if it did ask for molecules, you wouldn't.
If it had said molecules, we would have done everything the same, but we'd have left off that last step. Question on that one? All right. All right, take a few more minutes, work on those others, and then we'll run through them as well.
You erased one of the ones up there, by the way.
Without doing it?
Yeah, it was how many bonds are in CH3COOH. How many pi bonds?
Oh, the pi bond one, yeah, okay. Yeah, let's go ahead and do that. So for something like that, we're going to have to draw the structure. And the thing about the formula being written like this, the reason that these carbons are separated, it's not just C2H4 or O2, is it's telling you structurally how these are attached. You've got a carbon with 3 hydrogens. You've got your next carbon. And you've got to figure out how to attach these things. And you can play around with it in different ways. I don't know that there's a best way to go about it. But what you're going to end up with, in order to get every element its preferred number of bonds, you're going to end up with this. Because that way the carbons have 4 bonds. Both of these oxygens are on the same carbon. All the oxygens have 2 bonds, and so forth. This would be your structure. How many pi bonds? 1. How many sigma bonds? 7?
9.
No, just 7.
I said 7. 7 sigma bonds. 7 sigma and 1 pi in that total molecule. Question on that? All right, do the others. Did anybody come in and not get their exam back? All right. The one that's over there in green, I'm going to copy that here to the center board, just so we have room to go through. So I'm not changing anything, I'm not adding anything. Ready to go through the 4 on the right? Yes. All right. So to start with, we've got this one. You're asked about spectator ions, which means you need to think your way through net ionic equation. And the key to doing that is knowing your strong electrolytes. Strong electrolytes are strong acid, strong base, and salts when they're aqueous. So the first thing to do is skim through the labels. Aqueous, 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 liquid. That's not going to be in dissociated form. CO2 is a gas. That's not going to be in dissociated form. That much is absolute. But it's the ones that are labeled aqueous that you have to run through this checklist, and metal, non-metal, this is a salt, so that's actually existing in dissociated form. This is an acid. Is it strong or weak? Strong. So that's going to be an ionized form. Metal, non-metal, this is another salt. It's going to be in dissociated form. That's the ionic equation. And net ionic is where you go through and you throw out the spectator ions, the things that go through completely unchanged. And who does that? NO3 starts as an aqueous ion, ends as an aqueous ion, so that's a spectator ion. And the potassium. And that's it. So potassium and nitrate are your spectator ions. Question about that? All right. One change here. I'm gonna, well, what if, just for pretend, what if this had been HNO2 instead of HNO3? Would that change anything?
It's not gonna change.
It's going to change a lot,
No, I mean.
because now you're dealing with a weak acid, correct? And
Yeah.
weak acids don't ionize completely. And so in that case, I'll put this up here above. This would still be separated. But your acid would not. That's different, correct? The strong acids are separate, but the weak acids are not. Don't just automatically separate everything that's aqueous. Plus water, plus CO2. What do you have as spectator ions now? Only the potassium, right? You have NO2 negative on the product side, but you don't have NO2 negative on the reactant side because that's a weak acid. Do you see what the difference between those two? Question on that. Sometimes people get in the habit of automatically separating everything that's aqueous, and that's not correct. If it's aqueous, that doesn't mean separate. It means run it through your checklist. Maybe it's separated. So you've got to have your strong acids and strong bases memorized. If you haven't done that, now's a good time to do it, all right?